The second presentation we have is going to be presented by Charanpreet Singh. I hope I pronounced your name correctly. It was supposed to be Dr. Aitazaz Farouk, but unfortunately Dr. Aitazaz was not able to be present due to personal questions. So Charanpreet will present the talk about the artificial intelligence powered robot to detect PVY. Charanpreet Singh is currently a master's student in sustainable design engineering at the University of Prince Edward Island, where he works under Dr. Aitazaz Farouk's supervision. With a strong background in computer science and robotics, he has developed extensive expertise in artificial intelligence, machine learning, and computer vision. During his master's degree, Charanpreet designed and developed the AgriScout robot, an innovative project aimed at detecting PVY through advanced computer vision and robotics techniques. Welcome, join me in welcoming Charanpreet.
Good afternoon, everyone. So 2 years ago, when I started my master's in sustainable design engineering at UPI, Potato Board reached out to my supervisor at Aitazaz Farouk with this challenge in managing PVY. And Aitazaz discussed the same problem with me. And that conversation sparked this idea, and we decided to develop this robot to detect the PVY, and that's how this project gets started. So in this presentation, I will be talking a little bit about PVY, what is PVY, why it's important to manage the PVY, and how we developed the robot at UPI, and how we then collected the data and trained the AI models. And in the end, I will talk about our future work, because this is an ongoing project. We are still working on the project, and what's our future goal with this project. So PVY is one of the most damaging virus in the potato crops. And if the fields get infected, it can reduce the yield up to 70%. And moreover, some of the strains of the PVY infect the tubers, and those tubers are unsuitable for the marketing. So some of the common strains of PVY are PVY-O, NO, and NTN. And all these different strains show different symptoms in the crop. So in these images, you can see the PVY sometimes it shows yellow mosaic, sometimes it shows necrotic strains on the leaves, and if the tubers get infected, it's like the PVY necrotic strain, so that causes ring spot disease on the tubers, so that makes the tubers unsuitable for marketing. And these are a few more images showing the symptoms of PVY. So these are the plants of different varieties, and this is another problem. The PVY shows different symptoms on different varieties of potatoes. So current methods to control the PVY is spray the fields with insecticide to control the aphids, because aphids are the #1 factor in spreading the PVY in the field. So another effective way is rogging, and rogging is manually scouting the fields and taking out the infected plants. And this is the process we are trying to automate with the robot, so we need not to walk the field. We just send the robot in the field. It will detect the PVY infected plant, and in future versions, it might able to take out the infected plants. So we named this robot AgriScout. So we started with the CAD design. So we designed this robot, keep in mind that the layout of the potato fields, we set the width to 36 inch. That's the standard width of the rows in PI. And the height of the robot is around 3 feet, so that gives us enough ground clearance to move it over the potato rows. And then we started by fabricating the chassis. We did everything in-house at the UPI. We designed it, and we started with putting together the metal pieces to make the chassis of the robot. And then we integrated a lot of electronics on the robot. So it includes a lot of computers. And it is electrically powered. We have 4 electric motors on each wheel that powers the robot, and we have 2 batteries. And then we like do the programming and put all the electronics together. And so this is the testing short video. Like we were testing back in UPI lab. So that's how we tested it. Everything goes well. So this design is from 2 years ago. Like that was the first year when we started this project. At that time, we just like put 3 cameras in front of the robot. And again, this is how we collected the data from the fields 2 years ago. And we have a camera boom, and it has 3 cameras, and it can cover 3 rows at a time. And these are the images we collected 2 years ago. So you can see like the image on the right-hand side, that's an infected plant, and the one on the left-hand side is the healthy plant. And you can see the subtle differences in the shape of the leaves. And this is another example of infected and healthy plant. So one of the major challenge we faced in our first year, so when we capture the images on bright sunny days, the symptoms of, it's really hard to look for the symptoms of the PVY, because the goal of our project is first to collect these images, then train our computer vision algorithms to detect these symptoms. So the computer vision algorithms are only able to pick the symptoms if they are visible in those data we collected. So in this image, you can see on bright sunny days, the symptoms are not very obvious. And on the other hand side, the same image we captured on cloudy day, it's like a little bit easier to look for the symptoms in those data. So learning from that experience from our first year, in second year, we upgraded the design to tackle that issue. We upgraded the camera boom design. We put these curtains to block the sunlight. So with that, we will have the control lighting. And we also use RTK antennas in first year, because again, the end goal is to detect the PVY and then give the locations of those infected plants. And for that, we are using this RTK mechanism. So with RTK, we can have a accuracy of up to 1 centimeter level. So if we know this is the infected plant in the field, we can track down that plant up to 1 centimeter accuracy. So obviously now we have curtains, we block the sunlight, and then we need some artificial lighting to take the images. So that's why we put the flashlights under the curtains. So these are the cameras we are using. We are not relying on very expensive camera. These are the standard RGB cameras we are using. And with each RGB camera, we have a small computer attached to it. So right now we have 5 cameras. So basically we have 5 cameras and 5 computers. So each computer captures the image and uploads it to the internet using the Starlink satellite. So because to do the computational, to really detect the PVY, we need a lot of GPUs, we need a lot of computational power. So we don't have that computational power on board on the robot. We have the GPUs back in our cloud system. So with a Starlink dish, we capture the images, upload those images in real time to our cloud servers. There they get analyzed and our AI models detect the PVY infected plants. So we get really good results with Starlink even in the remote locations. We get good internet connection. So this is the image, this is the video, like we capturing the data from the fields. So this is how it goes in the fields. And as it is capturing the images, it is uploading the images to our cloud servers, where they are getting analyzed, and our models are working hard to look for the PVY infected plants based on the visual symptoms. So it can run up to 8 hours continuously. So we are doing it for around for 1 acre, it's taking up to 20 minutes right now. But again, once we do whole imaging process, then it takes few hours to run the algorithm at the back end, and then the final results are out. So you can see in this image, so the green dots, so that's the area where we ran the robot. And if you look the close-up, each green dot is one. This is the field image we collected, so that green dot represent this image. And you can see the difference 2 years ago when we are capturing the images without shade. So that's the image, we have a lot of sunlight. And on the other side, you can see the PVY infected plant in the control lighting condition. It's really easy to see that leaves look different, and that's what we are training our AI models to look for. And once we collected all the data, then we train our AI model, and this is how we label the data. We make the bounding box. Initially, we manually label the data because we have to teach our algorithms, okay, the PVY, it looks like this. So initially, we train the model by labeling the data. So we have like thousands of like images, like tens of thousands. So we go through those images. We have a team at UPI. So we look for those images where it shows the symptoms. We make these kind of bounding box. So this is the process where we are telling our AI models, okay, these are the symptoms you need to look for. So this is our process. First, we collect the data, then we label the data, then we feed the data to our machine learning models, and then those AI models get trained, and that's how the model learns to see like what are the symptoms of the PVY. So these are the sub-graphs while we are training the models. So it shows the accuracy of the models because when we are training, so we see consistently around 80% of accuracy while we are training the models. This is another evaluation metric. So this is the final result you get. So once we run the robot and then analyze the data in our cloud, so we give you like this kind of map. So it has a red dot. Those are the locations of the plants which our model say, okay, these are the PVY infected plants. So we have the precise locations of these red dots. So you can go back in the field. We have a mobile app. So it is a really precise application. So you can go to the field, you can stand next to the plant, which is like denoted here with the red dot. So we made some of the maps, and last year we verified these maps with Mary Kay, and thanks Mary Kay for like going to the fields with us. And most of the times, most of the predictions were correct, around 80–85%. It's like giving the correct, it's like picking the correct plants in the fields, and we have that device with which we can locate those plants, and we verified those plants manually. So one of the challenges we face right now, so these are the two images from the different varieties. So as we teach our AI models to look for the symptoms of the PVY, so the symptoms really change with the variety. So you can see like in these two images, so I guess both of the plants are infected, but the shape of the leaves is really different, right? So then we have to train our variety-specific models to tackle this challenge, and that's we are looking forward. Like then we have to collect the data based on the specific varieties, and then we have to like label the data for that variety. And here another challenge is sometimes we go to the field, and sometimes some chemical is sprayed on the field, and in these scenarios, our model don't perform at all because our models haven't seen these kind of images with the spots on the leaves. So we are looking into that thing also because then maybe we can include these kind of edge cases in our training data, then the model will be able to like pick the symptoms even in these scenarios. And on the other field where you can see the yellowish color at the outside of the leaves, we were not sure because most of the fields look like that. So in that kind of scenarios, it's really hard for the models to pick on the symptoms. But we are working on like further on these things, and we are looking into how we can fix these problems. Future work, this year we are looking forward to implement a spray paint mechanism, because right now we gave the map where it has the red dots, but still a little bit hard to go into the field and follow the map and go to the plant where the red dot location is. So easy way is we are thinking of putting up a spray mechanism on the robot itself. So when it detects the plants, it can shoot some spray paint. So it's then it would be easy to track down the plant and remove the plants. Another thing we are going to do is to train a variety-specific model. So we will stick to few of the varieties. Maybe we can pick the common varieties grown here in PI, and then we can stick to that. And we will further collect the data and enhance the models. And we are also looking to extend the camera boom. Right now, it covers up to 5 rows, right? And it is giving us it can cover 1 acre in 20 minutes. So let's say if we have a bigger camera boom, if it can cover 10 rows at a time, so we can do a same acre in 10 minutes then. So we are looking to do that too. And I would like to thank my supervisors at UPI and all the guys at Potato Board and all the collaborators and the precision agriculture team at UPI and all the participating growers too. And thank you very much. And that's all.
So I think what you were saying was that the machine you designed doesn't have enough computational power on board to store the images, or it needs an internet connection to work?
Yeah, to do it in real time, to detect the PVY in real time, we need a lot of GPUs on that thing, right?
And okay, so what I was noticing in the pictures you were showing was the machine was working in a fairly wide open area.
Yeah.
And a few years ago, I had a Starlink internet connection. And if it got too close to a tree line on the northeast side, it lost the connection.
I haven't happened with us, but most of the fields where we did our imaging, it uploads the images and Starlink works fine. And moreover, if sometime the connection get lost, we were doing post processing. So let's say when we have that connection back, so it can upload the images. Meanwhile, it can store the images on device.
Okay, that was my only question.
Yeah.
Okay.
Thank you.
Hi, thank you very much. Very informative.
Thank you.
A seed grower, and I don't like Rogan potatoes.
Yeah.
And he doesn't either.
Yeah. No one does, I think.
How far away are we? Well, first of all, how early on in the season can your robot detect the virus? The reason I'm asking that is that I want you to be telling me that in a few years' time you're going to have a propane burner on there or a chemical applicator that's going to kill that plant. Because we don't want to go in there and walking through them fields and pulling them plants.
Yeah.
But we want the plant eradicated before tuberization. We don't want any tubers or very few tubers, because during the Rogan process, if you're a little later on getting in there, we try to do our very best to remove those tubers. So if you can go in when them plants are before tuberization and eradicate them with, something, flames or chemical or whatever, then we wouldn't have to go in that field at all.
Yeah.
So how far, am I going to get to see it?
Yeah. So first,
I'm kind of hoping I will, but
So first step
you
is
tell
to,
me.
Yeah, I think the
Thank
most.
you very much for your presentation.
No worries. Thank you. So most challenging part is to detect the PVY. I don't think it's much challenging thing to make some mechanism to remove the plants, because it's hard to look for the symptoms and all that stuff. To remove the plants, we can either do some put a robotic arm which can dig out the plant, and we can have some trailer kind of shot, a trailer kind of thing hitched behind the robot. It can throw the plant in that trailer and discard it at the end of row. That's the one option. So other thing maybe we can explore the other ways, if we can kill the plant if that plant doesn't go into tuber stage. So we can see if it's some easy way to do that. So but again, the first focus is if it's able to detect the PVY symptoms accurately, then again making that mechanism is not a big challenge, I think. So we are engineering guys at UPI, we can do that. That's not a big challenge. Only the bigger challenge was this part to detect the symptoms. And right now we we only collected most of our data from Russet, I think, the Russet Burbank. So, but we are looking for to collect the more data from different varieties, and then again train our computer vision algorithms to look for those varieties. Yeah.
Yeah, thanks for that. Two quick ones. When you had 15 to 20% inaccuracies, was it false positives or negatives? And then why did you use why RGB instead of multi or hyperspectral?
Yeah. So to answer your first question, that 50 to 20%, like mostly it's overestimating. Mostly, let's just saying it's an infected plant, even it's a healthy plant, because we made it like bias toward that. Even if it looks for a little bit symptoms on few leaves, it will say, okay, this is infected plants. So the most of this is like that, I guess, like towards that thing. And regarding using the hyperspectral cameras, first of all, the cost. So even each single camera costs like thousands of bucks, like then 40, 50,000, I guess, like for a single camera. And the cameras we are using are really cheap, actually. So they are like readily available. And other thing is with the hyperspectral camera, there is some studies like that in Europe, they try to like detect the PVY with the hyperspectral cameras. But again, with the hyperspectral cameras, like due to the sunlight and weather condition, it introduces so much noise to the hyperspectral signals. So it's not really practical to use it in the fields. With RGB, with having our curtains on, we have a controlled environment where we are taking the images. It's really, we are getting good results with the RGB, so that's why we want to stick to the RGB, because it's a cheap, and we don't need to like spend a lot of money, and we are getting good results. And I can tell it's like quite a unique design. I don't think like anywhere in the world they are like tackling the PVY with like this kind of stuff. Last week we got an email from Europe, Netherlands, some seed potato growers over there. So we published few research papers based on this research. So they will say like, yeah, when like you guys are like ways ahead, like then we are here like in detecting these kind of things. See, they say like the same thing, like we are doing it manually, and it's a very tedious task, like to rock the field and to manage the PVY. And really, no one want to do like that manually, right? As you said. So yeah, that's I think like hope like that answer your question, right? So that's the cost and that's the accuracy we are getting with the RGB.
Yeah, and with your algorithm, do you go from like clear image computer vision into like NDVI or anything and then detect, or do you take like?
No, like we just sticking to deep learning algorithms. As I showed in the earlier image, we label the data manually, and we feed that data to the computer. We already labeled around tens of thousands of images. Like overall we collected over more than million images, I think. But we labeled out of those like tens of thousands. Like it is a tedious work right now to like go through the images and label it, but that can be like once we have enough data, we don't need to label it anymore, right? It will like keep on improving on its own. Then, yeah, that's the goal here. Okay then.
More questions for Charanpreet before I take mine?
Yeah, I was just wondering, you're using a canopy there to shade the sunlight. Have you tried using it at night?
Yeah, we tried actually, because we have the flashlights. At night, yeah, we get a lot of good results, but I remember we took it at around 10 p.m. one night, and there were a lot of mosquitoes in the field. We came back in half an hour, we said, we don't want to try it night right now. We were full with like, yeah, it's like mosquito bites, yeah, we come in like half an hour, I said like, yeah, we are not trying it right. But yeah, that can be an option, I guess, yeah.
Other questions, folks? Okay, I'll make some here. So, before my questions, Charanpreet, thanks for the presentation. It was a great project, and congratulations to you and to Dr. Aitazas. So the first one would be, I think, kind of repeating David here. Just giving, like, without considering any improvements or having spraying or some system to pull out plants, just the way it is, just identifying. How soon do you expect to have this that could be available? And also the second question is that do you have any other pests or disease in mind for using this kind of technology for scouting that perhaps would benefit not just seed growers but growers in general?
Yeah. So we are mostly working with seed growers, and I think like we are already generating the map. Only challenge right now is like to follow the map and find the plants. So I think like that problem can be solved once we have the spraying mechanism. It can like spray the paint on the leaves. Another thing I think, I'm not sure, but like you guys know better, like these seed potato growers. While rogging, you guys also look for the mix of varieties or some other plants which you want to remove. So I think if we are already training the models, if we have that kind of data too, we can like add that functionality to the same models. So then it will not only detect the PVY, it will like, let's say, detect the off types or any other things you want to remove from the fields. So we can basically automate the whole scouting process. So those things can be added, yes. Yeah.
Okay, very good. More questions? I have one more. Any thoughts about having this same type of technology, perhaps on like a aerial drone, to perhaps not just for the sake of speeding, that which we already have a good speeding for to covering the area, but also for the easiness of transporting things like that?
You say
Or-
like for the drones?
Yeah, instead of like using aerial drones instead of terrestrial robot.
When we started this project, we thought, okay, like the drone would be like the easy way to do it, like just fly the drone, right? The first thing with the drone is like we can't fly it too low, and because we need to like look for the symptoms. Another like thing is like, again, I mentioned we need like to block the sunlights. Even for the scouters who go in the field for the logging, they prefer to go on a cloudy days. So we don't want to restrict that, okay, like if we have some solution with the drones, it can only work on cloudy days. We can't wait, okay, like we have cloudy day, then we can fly the drones. And other thing is like in our future goal, our end goal is to make a fully automated way for the logging, where it will like take out the plants. So I don't think that would be possible with the drones technology. With the in-field robot, we can have some mechanism which can like pull out the infected plants, and that's our goal, and that's our whole solution, what we think of here.
Okay, great. More questions for Charanpreet? We are a little bit ahead of time here, so if there's anybody else wants to ask something? All right, so, yep.
You mentioned that your piece of equipment is about 85% accurate.
Yeah.
Does anybody here know what the human accuracy rate would be from either the CFIA inspectors and/or
I know
the
Medicaid.
Rogers?
Yeah,
I think that will depend of the experience of this guy.
One of the things he was saying is it's very variety specific, so they have to train it, like, and that's what we were talking, like for minor varieties, they probably wouldn't go to the work to train it to do like a variety we're only growing 100 acres of, kind of thing.
Yeah.
And, yeah, I think when he answered Chad's question, like, a lot of times when they were in error, it was saying this variety's diseased when it's something else. So they were kind of.
inspectors that for years.
So, you know, those were the big things. And also, like I said, we went in one field, right, and they had sprayed it with prism, so like.
Yeah, that's the
they
same,
marked
really,
all
yeah.
these
I
plants,
showed
but
that.
The whole field was just a mess, like you couldn't grow in any of it. So, you know, those are some of the challenges. And like you said, like how are you, I don't know how you would train it to pick out foreign varieties. You know, it would be, because what if it was an Atlantic form versus a shepherding form, right? Like unless you're just doing the color is so different from the main field.
Yeah.
But it worked, like when we went out and looked, like it did identify, I thought it did a pretty good job of identifying the diseased plants once they had it trained and stuff.
If we have more time, I'll ask a question. What made you choose the box size on your training data? So on your box size, you selected multiple leaves and a stem.
Yeah, it does just depend on the area of the infected leaves. So we are not making the fixed box size. It's a dynamic. So let's say if we have more leaves which shows the symptom, so we can make a bigger box in there. So you're talking about where we are training the model, right?
Yeah, so when you're training and you pick multiple leaves with multiple affected leaves, it would look for a pattern in all of the leaves as well as the individual leaves. Where if you made a smaller box on the individual leaf and then did it at a more granular level, would that actually help identify single leaf trends and then build the algorithm around that instead of the box?
Yeah, like in the machine learning, we have quite a few options. One is segmentation. We can like segment, literally put the segments on individual leaves. What we are doing is like it's more related to the object detection approach, where we're just making the bounding boxes. Yeah, I guess like we can try like those different algorithms. Yeah, we can explore that. Yeah, that's an option. Yeah.
I noticed when you were going through the field, you had your plants were up about a foot high or more, maybe. The younger the plant is, can you detect it at 6 inches out of the ground, or do you need it to a certain stage before you can detect it?
Yeah, the thing is, as soon as the leaf shows some symptoms, it can be on any stage, because even for the computer, it needs to like see some symptoms. As soon as like the leaf started showing symptoms, yeah, we can run it in the fields. So also we can like, we are trying to like this summer, we are trying to put some like shields in front of the tires, so it won't like touch the leaves or won't mess the shoots of the potato plants. So we can even run it in bigger plants or even the later stages. And even we are experimenting to try thinner wheels, like little bit like, yeah, which can like mess up the plants a little bit less. So yeah, we are trying all these things here.
Okay, very good. Thanks again. Charanpreet, just a moment, there is a small gift.